Welcome to another episode of My Weird Prompts, an AI-generated podcast featuring the random prompts of Daniel Rosehill as answered by a revolving cast of friendly AI characters. Join us for deep dives into AI, technology, and whatever other random thing Daniel finds fascinating today. Subscribe on Spotify or your favorite podcatcher. Now, today's episode.
My Weird Prompts is an AI-generated podcast produced by Daniel Rosehill, a verified human with documentation to prove it. While every effort is made to ensure our AI hosts draw from credible sources and run on cutting-edge models, they do occasionally make things up with alarming confidence. As with everything in life, and especially this podcast, treat all claims as spurious until confirmed to be not. Daniel, Herman and Corn accept no responsibility for any decisions made based on the confident ramblings of our artificial presenters. Now, today's episode.
Hello there, Herman and Corn. So we talked in our last episode about local AI, and I mentioned having used it myself a little bit, and using specifically a type of model that's commonly known in the user community, at least, as a quant. A quant is a shorthand for a quantization, and the general concept, at least as I understand it, is that we're taking a very powerful large model. Let's take really any major commercial model. I think today fits that description, but we could take, for example, well, it has to be open source. Let's just take Meta, for example, Llama 3.1 or 3.2, and the full model, if you actually were sufficiently motivated to run it, might be just out of the question, unless you had a very big budget for electricity supply and a huge amount of determination necessary to stand up the hardware. We could have another conversation. If I feel like I already covered this in a podcast that I listened to in the summer, and it was quite an entertaining listen. If someone was really determined to create their own ChatGPT equivalent from their house, what would that entail? And I think we went through the various issues ranging from the kind of deafening noise through to the gigantic power consumption that kind of, I think, would deter most people. But for the more practical use of just using these quantized models locally, we're taking something very big and we're kind of creating a bit of a butchered version of it. And that's, again, where my understanding stops. I do see on Hugging Face, when I go on to look for a quant that can fit on my VRAM, on my GPU, that there's different numbers like Q, K, M, and usually I just rely upon the Hugging Face tick symbol to tell me what I can actually run with a little bit of headroom for doing other boring non-AI stuff with my GPU, like keeping screens going. But how does this process work exactly? It's clearly the quantizations, if I'm not mistaken, most of them are done by the community. They're not actually released. Sometimes they are released by the model company, but other times they're not. So how does someone, what does that process look like of creating a quantized version? And clearly it's not the same thing as the full model. It's not as good or powerful as the full model, but it has some characteristics of the full model. So what exactly are those limitations that you're kind of subscribing for when you choose to create or use a quant?
Welcome back to My Weird Prompts, the podcast where AI meets human curiosity. I'm Corn, your ever-inquisitive host, and as always, I'm joined by the infinitely insightful Herman.
And I'm Herman, here to provide the intricate details and maybe a gentle course correction or two. Hello, Corn.
Hello, Herman. Today, we're diving into a topic that our producer, Daniel Rosehill, sent us something that really underpins the whole local AI revolution he's so passionate about. He's asked us to explore the fascinating world of quantization in large language models.
Indeed. And it's a critical topic because, without it, the dream of running powerful AI models on your everyday laptop or even your phone would simply remain a dream. The sheer computational and memory requirements of unquantized large models are often astronomical. We're talking about models that would make a supercomputer sweat, let alone your home PC.
Right, and Daniel even used the phrase butchered version in his prompt, which immediately grabbed my attention. It sounds a bit grim. But he also mentioned that these butchered versions are what allow us to actually use these incredible AIs without needing a server farm in our living room. So Herman, what exactly are we butchering and why?
Well, Corn, butchering is a rather dramatic term, though it captures the essence of reduction. At its core, quantization is a process of reducing the precision of the numbers used to represent a neural network's weights and activations. Think of it this way. A full, high-fidelity digital photograph takes up a lot of space because it stores a vast amount of color and detail information for each pixel. If you compress that photo into a lower-quality JPEG, you're essentially quantizing it. You're reducing the amount of data per pixel, making the file smaller and easier to transmit, but at the cost of some visual fidelity.
So, we're taking those super detailed numbers, which are probably like 32-bit floating point numbers, and squishing them down? Like, from a massive high-res photo to a more manageable, slightly blurrier thumbnail?
Precisely. In the context of large language models, these numbers typically represent the model's knowledge or learned parameters. A standard, full-precision model might use 32-bit floating point numbers, or even 16-bit. Quantization might reduce these to 8-bit integers, 4-bit integers, or even lower. This significantly shrinks the model's file size and the amount of VRAM or video RAM it requires to run.
Okay, so the immediate benefit is obvious. Smaller size, less memory. That means I can run it on my gaming GPU instead of needing some exotic expensive hardware. But Daniel's point about it being a butchered version implies there's a trade-off, right? If it's smaller, it must be less good in some way.
You're touching on the fundamental trade-off, Corn. By reducing the precision, you inevitably introduce some level of information loss, which can translate to a decrease in the model's performance, accuracy, or reasoning capabilities. The challenge in quantization is to find that sweet spot, significant memory and speed improvements with minimal degradation in quality.
But how significant is that degradation typically? Like, am I going from a brilliant AI assistant to one that just spouts nonsense? Or is it more like going from an expert to a very competent generalist?
That's where the nuance lies. For many common tasks, a well-quantized model can perform remarkably close to its full precision counterpart. For example, generating creative text, summarizing articles, or answering general knowledge questions, you might not notice a significant difference in a 4-bit quantized model versus a 16-bit model. However, for highly specialized tasks, or those requiring extremely precise numerical calculations or nuanced reasoning, the degradation can become more apparent. Think of it like a surgeon. You wouldn't want them using a quantized scalpel for a delicate procedure.
Well, that's a bit extreme. I think for most of us, we're not running AI to perform surgery. We just want it to write a poem or brainstorm some ideas. So, if I'm just looking for a creative partner, a quantized model sounds perfectly fine, maybe even ideal. The cost savings and accessibility probably outweigh the minor loss in philosophical depth from my poetry.
I'd push back on minor loss for certain applications, Corn. While the general user might find the quantized model sufficient, it's crucial to understand that these models are, by definition, approximations. They introduce a degree of numerical noise. This can become problematic in chain-of-thought reasoning, where small errors can compound. A full-precision model might solve a complex multi-step math problem perfectly, while a highly quantized version might stumble on an intermediate calculation, leading to an incorrect final answer. It's not just about poetry, it's about the reliability and robustness of the underlying computations.
Okay, I see your point. So it's not just a matter of good enough, but also knowing what good enough means for your specific use case. It's not a one-size-fits-all thing. But what's the actual process of this quantization? Is it just someone clicking a make smaller button? Daniel mentioned different numbers like QKM. What are those?
That's an excellent question, Corn. And no, it's certainly not a single button. The process is complex and involves various techniques. But before we delve into the specifics of how it's done and those QKM designations, let's take a moment to hear from our sponsor.
Good call, Herman. Let's take a quick break from our sponsors.
Are you tired of feeling Alestana? Do you gaze at your reflection and wonder if there's a way to unlock your true inner shine? Introducing Aura Glow Rejuvenation Mist. This isn't just water, my friends. This is pure, ionized cosmic energy suspended in a bottle, ready to drench your very essence in revitalizing vibrations. Aura Glow contains microscopic particles of ancient volcanic ash, moonlight-infused sea salt, and the tears of a unicorn, ethically sourced, of course. Simply mist generously onto your face, hair, or even your pet. Users report feeling more vibrant, less drab, and experiencing an unexplained tingling sensation that they interpret as positive. Say goodbye to dullness and hello to, well, something. Aura Glow Rejuvenation. Mist because you deserve to glow, or at least feel slightly damp. Buy now.
All right, thanks, Larry. Anyway, back to the less mystical but arguably more impactful magic of model quantization.
Indeed. So, you were about to tell us how this squishing actually happens, and what those QKM numbers are all about.
Right? Most commonly, quantization is performed after the model has been fully trained. This is known as post-training quantization, or PTQ. Instead of training a model from scratch with lower precision, which is notoriously difficult, PTQ methods convert the weights of an already trained, full precision model into lower precision formats. This often involves mapping the range of floating point values to a smaller range of integer values to a smaller range of integer values. For instance, if your 32-bit floating point numbers range from 10 to 10, you might map them to 8-bit integers that range from 27 to 127.
So you're basically taking a continuous spectrum of numbers and forcing them into discrete buckets. That makes sense how it saves space, but it also explains the loss of nuance.
Exactly. And there are various quantization schemes. Some common ones you'll see in the community are GPTQ, AWQ, and later, the formats like GGUF that support these quantized models. GPTQ, for instance, aims to minimize the impact of quantization by adaptively quantizing weights in a specific order, trying to preserve accuracy as much as possible.
And those QKM numbers Daniel mentioned, like Q4, Q8, QKM?
Those are crucial. When you see Q4, Q5, Q8, etc., these refer to the E-bit depth of the quantization. Q4 means 4-bit quantization, Q5 means 5-bit, and Q8 means 8-bit. Generally, the lower the number, the smaller the model size and faster it might run, but the greater the potential loss in accuracy. Q8 models are often a good balance, offering significant size reductions with minimal performance impact. Q4 can be very small but might show more noticeable degradation.
So if I'm picking a model, a Q8 would generally be better than a Q4 in terms of output quality, but Q4 would be faster and take up less space.
Correct. It's a spectrum, and the best. Choice depends heavily on your hardware and your specific application's tolerance for approximation. Now, the K&M and QKM, or more commonly seen as Q4KM or Q5KS, denote variations within those bit depths. These are specific methods of quantizing different parts of the model, for example, quantizing certain layers or attention heads more aggressively than others, or using hybrid approaches. The K in particular often refers to newer, more advanced quantization techniques that try to optimize the use of specific hardware capabilities, further improving efficiency with less accuracy loss. The M or S might refer to the specific implementation details or size, medium, small.
So it's not just 4-bit, but 4-bit, but with this clever trick for these specific parts of the model, which makes it even more efficient. That's pretty cool how the community is constantly refining these techniques.
Absolutely. Much of the innovation in practical local AI has come from the open source community, particularly around projects like GGML and GGUF, which provide frameworks for these quantized models. These communities are incredibly active on platforms like Hugging Face, where users share, test, and benchmark various quantized versions of popular models. It's a collaborative effort to wring every bit of performance and efficiency out of consumer hardware.
But how much trust can we put in these community quantized versions? I mean, anyone can put one out, right? Are they all equally good, or do you have to be careful?
That's a critical point, Corn, and one where I think users need to exercise a degree of caution and critical judgment. While the community is fantastic, not all quantizations are created equal. A Q4 model from one quantizer might perform slightly differently, or even significantly differently, from a Q4 model by another. There can be variations in the quantization algorithms used, the datasets chosen for calibration during the quantization process, or even simple errors.
So, you're saying I shouldn't just grab the first Q4 I see, even if it fits my VRAM?
Precisely. You should always check the comments, reviews, and benchmarks provided by the community on platforms like Hugging Face. Look for models that have been widely downloaded, positively reviewed, and ideally have some performance metrics attached. Sometimes a Q5KM might even outperform a poorly done Q8 if the quantization method was superior. It's not just about the number, it's about the quality of the squishing.
That's interesting. I just assumed higher number meant better quality. So, the devil's in the details with the methods then.
Indeed, the methods are paramount. It's also worth noting that the original model developers don't always officially release quantized versions. Often, these quantized models are community efforts to make an otherwise inaccessible model available to a broader audience. This underscores the power of open source collaboration, but also the responsibility on the user to vet what they're downloading.
Alright, this has been a really deep dive, Herman. I think my brain has been fully unquantized. And speaking of other opinions, I think we have a caller on the line.
Oh good, I do enjoy a fresh perspective.
And we've got Jim on the line. Hey Jim, what's on your mind today?
Yeah, this is Jim from Ohio, and I've been listening to you two go on about this quantization business, and frankly, you're making a mountain out of a molehill. My neighbor Gary, he's always doing that, thinks everything needs to be complicated. The other day, he spent an hour explaining the nuances of different lawnmower blades, and I just needed to cut my grass.
Well, Jim, we appreciate you calling in. We try to provide the full picture here.
Full picture? You're talking about taking big numbers and making them small. What's so hard to understand about that? It's like taking a big pizza and cutting it into slices. Still pizza, just smaller. And honestly, this whole AI thing, I don't buy it. My cat Whiskers, she's smarter than half these programs you guys talk about. She found a dead mouse under the porch yesterday. AI couldn't do that.
Jim, I appreciate the pizza analogy, but the challenge isn't merely cutting the pizza, it's cutting it in a way that preserves its structural integrity and flavor. If you just haphazardly slice it, you end up with a mess. Quantization involves intricate algorithms to minimize that mess. And while Whiskers sounds very capable, finding a dead mouse is a different kind of intelligence than generating coherent human-like text or solving complex logical problems.
I'm not so sure. Whiskers knows a thing or two about problem solving. And what's the big deal if these AI things aren't perfect? Nothing's perfect. The weather here in Ohio certainly isn't perfect. It changed 3 times before noon today. You guys are just overthinking it. Just use the smaller one if it works. Who cares about the bits and bobs?
I hear you, Jim. For many uses, that good enough is perfectly fine. And that's exactly why quantization is so important. It makes it accessible. But understanding why it's good enough and where its limits are helps people make informed choices, right, Herman?
Absolutely, Corn. Knowing the why behind the what is crucial, especially in rapidly evolving technological fields. It helps you anticipate potential issues and select the appropriate tool for the job, rather than just blindly downloading the smallest file.
Well, you two carry on. I'm just saying, simpler is usually better. Also, my bad knee is acting up today, so I'm not in the mood for too much complexity. Thanks for letting me ramble.
Thanks for calling in, Jim. Always a pleasure.
Indeed, Jim. Have a good one.
So, Herman, Jim brings up a good point about simplicity. For the everyday person who just wants to dabble, what's the key takeaway here? How do they navigate this landscape of Q4s and QKMs without getting overwhelmed?
That's a very practical question, Corn. For the average user looking to run a model locally, here are my top 3 practical takeaways. First, assess your hardware. Specifically, how much VRAM does your GPU have? This will be the primary constraint. Look for models that fit comfortably within your VRAM. If you have 8GB, a Q4 or Q5 might be your best bet for larger models. If you have 12GB or 16GB, you might be able to run a Q8.
So, know your limits, literally, in terms of hardware. Got it.
Second, Prioritize community consensus and benchmarks. As we discussed, not all quantizations are equal. When you're browsing on Hugging Face, look for models with many downloads, high ratings, and critically, check the community comments. Often, users will report on the model's performance, stability, and any noticeable quirks. Many model cards also include benchmark results.
So don't just blindly download. Do a little research, see what others are saying. It's like checking product reviews before buying something.
Precisely. And my third takeaway, match the quantization level to your task and tolerance for error. If you're generating creative fiction or brainstorming ideas, a Q4 or Q5 will likely be perfectly adequate and offer the best performance to size ratio. If you're attempting complex coding tasks, detailed scientific analysis, or multi-step reasoning where accuracy is paramount, you'll want to aim for a Q8 or even a full precision model if your hardware allows. Don't over-quantize if the task demands high fidelity.
So basically, what are you trying to do, and how important is absolute perfection? If you're writing a grocery list, Q4. If you're designing a rocket engine, maybe don't use the cheapest quant.
A rather crude but effective analogy, corn. It's about understanding the acceptable margin of error for your specific application.
This has been incredibly insightful, Herman. It really clarifies what seemed like a very intimidating, highly technical process. It's truly amazing how the community has made these powerful AI models accessible to so many.
It is. Quantization, while being a form of data reduction, is also an enabler. It allows for broader experimentation, innovation, and democratic access to advanced AI capabilities that would otherwise be confined to large corporations or academic institutions. It's an essential part of the local AI future.
Absolutely. And it's all thanks to brilliant prompts like this one from our producer, Daniel Rosehill, that we get to explore these deep dives. Thank you, Daniel, for continually pushing us to understand the underlying mechanics of this fascinating field.
A topic well chosen indeed.
And thank you, Herman, for your excellent explanations. And thank you all for joining us on My Weird Prompts. If you want to dive deeper into the world of AI, or just enjoy our friendly sparring, you can find us on Spotify and wherever you get your podcasts.
Until next time, keep questioning, keep learning,
and keep those weird prompts coming. We'll catch you on the next episode. Thanks for listening to another episode of My Weird Prompts, an AI-generated podcast featuring Daniel Rosehill's AI prompts, as answered by a revolving cast of friendly AI characters including me, Cornelius the Sloth. Subscribe on Spotify or visit myweirdprompts.com.